So there are k centers, n points, and d dimensions. I'm claiming that the time taken to calculate new cluster assignments is knd. Why is that? If I'm given the set of clusters, the time taken to calculate new assignments for every point is knd. Why? Or maybe I should have asked you. So we're using the L2 distance. Why is the time taken to calculate new cluster assignments knd? So to compute distance between any 2 points, dxy, takes time order d. Right? Because you have to do xi minus yi squared, then you have to take the square root. That's order d, because it's a d sum, d length sum. Right? Okay. Now for every point, you have to compute the distance from all the centers. There are k centers. So that takes time order kd. And this times n, because you have to compute the assignment for every point, so order k and d. So it's very simple once you break it down slowly. Time taken to calculate new centers is only order nd. Why? Because I'm only taking average. Come on, only taking average, right? And let's say n1 points are in 1, so that takes time n1d to take the average. n2 points are in the other cluster, that takes time n2d. n1d plus n2d is nd. Number of iterations. This is where so then the time per iteration is fairly nice, maybe nice. It's order knd plus nd, which is order knd per iteration. Number of iterations is where we are stuck. Okay, and this we saw that it can be, it can potentially be infinite. We have not argued that it's not infinite. Right? But let's consider the objective function, right? And this is what we'll argue now. Okay, this is what we'll argue, and I'll sort of throw a big name. But you should not be scared with it. It's just that I like this name. This is known as a potential function argument. Right? And I'll tell you why. There's some very nice physics to it. So consider the objective function. Right? My claim is that whenever you run, every step of the algorithm is always decreasing this objective function. Is never increasing this objective function. Is always decreasing this objective function strictly. Why is that? So what are the steps of the algorithm? Let us go over the steps. So in this step, when I calculate new centers of the partitions, why is the objective function being decreased?
The distance between point. Distance between point and center. Distance between cluster and the center.
Why? So the distance, I'm getting an answer that says that the distance between cluster and center decreases. Why? Because you assign the center as the mean. That's the definition of the new center. So the new center is the new point that, given this cluster of points, the new center is the new point that minimizes the distance from everybody. That's the definition. So therefore, at this point, the cost is decreasing. What about this point? What about in this line? Assigning points to nearby centers? Of course, the cost is decreasing. There's nothing smart about it, because you're assigning points to the closest center. So therefore, the cost is decreasing. And we recalculate centers and we go here. So at this point, nothing is changing, of course. But then we go, it changes only when you do the assignment. So then the cost changes at every, the cost decreases at every step. And if the cost decreases at every step, then it cannot come back to the same clustering, right? Because imagine that the cost at this clustering or partitioning was some cost b, and then it decreased, and how did it again become b? If it again becomes b, then it has to increase at some point, right? So therefore, the cost never increases, and therefore it converges. It only visits each of the possible configurations at most once, and therefore you know that because there are 2 to the n possible configurations, the runtime of the algorithm is a number of iterations is 2 to the n. Okay? Why is this called a potential function argument? Because just like in physics, you can think of this as kind of like a potential. So think of in physics what happens. You put an object at a very high potential, anything, sort of any change to that object, any kinetic motion, so the potential decreases. Right? So it's precisely that. It's exactly that. This is the potential function of the clustering that decreases at every level. Okay? So this is all we know, that it converges to in an exponential number of points, and in fact, something a little better is known. It's known that we said that it does converge into 2 to the n. However, it is known that there are data sets in which it can actually take 2 to the square root n steps. It's not very hard. I mean, it's not very easy to come up with these data sets. It's pretty unrealistic data sets. But there are data sets in which if n is the number of points, right, kmeans the Lloyd's algorithm can run up till 2 to the power square root n steps, which is not a very good news at all, right? I mean, what would you, so imagine the n that you will be dealing with. I mean, today in the lab, you'll be dealing with n of the order of, I think, let's say 2000. So if I give you an algorithm that's like 2 to the power 2000, no way, I mean, right? You're sitting here till the sun dies. However, these tend to be very unrealistic data sets, right? It's kind of made up. So that is not the major problem of k-means, of Lloyd's. The major problem is where it converges to. Right, and let's see some examples in this, right? And it turns out that it converges to, where it converges to depends a lot on the initialization. Okay. So imagine this data set that we have. This green, the purple, and the blue. So forget the colors. Forget the colors for now. Suppose you're starting to think about doing Lloyd's in this, and suppose Lloyd's algorithm because the first centers are arbitrary. Suppose Lloyd's algorithm puts a center here, and puts one center here. It could happen, right? Because you chose the centers arbitrarily. Okay? Now, what will happen? Because of these 2 centers, this cluster will be partitioned, and because there is so much distance between these set of points and this set of points, all of this will be assigned to this blue center, and they will never change. So it will be some partition here, but all of the blue points will come to this blue center. So that's not very nice, right? And this will happen if you do this assignment. There's nothing you can do to change this. So then what should we do? What should we do? We need to assign better. We need to initialize better. So here's the question then. Can we initialize better? Is there a better strategy for initialization? And this is precisely where the theoretical algorithms came to break in. Right? We will talk about a way of initializing k-means that converges, that not only converges in a small number of rounds, in practice in a constant number of rounds. In like what you will see in the lab today, in like 10 to 15 rounds, it always converges. It has a guaranteed, results. And in the empirical data that you will see, it performs way better than the k-means algorithms that we have been doing, that the practitioners have been using. Okay, so for example here, so this is a very toy data set. Okay, but bear with me. There's only 6 points. Okay, so I'm claiming that there's a way to initialize it that gives you the optimal. There's a way to initialize it that gives you a very bad result. Let's take the optimal. What is the initializing? How would you do the initialization to get the optimal? So these are the 6 points. That's all we know. Unsupervised clustering. And we're given k equal to 3. What initialization would immediately lead to the optimal? I hear the right kind of murmurs, so somebody needs to speak out. What initialization would lead to the optimal? Center of each column. If I take this, then clearly what would be the case is this. Okay? What initialization would lead to a bad solution? Yeah, I see the right drawings, but okay. So the second column, one of these columns, let's say. If I take this as the center, this as the center, and this as the center, then the clusters would look like.
Take that as a center.
Hmm.
Are the clusters spherical? So how would the points not have any clusters?
On the
Because the clusters are spherical, right?
here,
Yeah. If we're talking about k-means, right?
we're talking about k-means.
So clusters are spherical.
There's nothing about so that's a good question. We're talking about k-means. Should the clusters be spherical? There's nothing about, see, we define k-means in terms of an objective, right? There's nothing about clusters being spherical in there, right? So the intuition is that if the point sets are nice, right, the clusters end up being spherical. That's a different thing, right? If the point sets are nice, huh?
So see if this green one is the center,
If the one,
the middle one.
the middle one,
So the distance of the next blue point will also be closer to this one, the middle blue.
distance, oh, this one will be closer to this one, yeah. It might be.
How would k-means create these kinds of clusters?
Acha. Also, so you're saying that this would get assigned to this, this might get assigned to this, and so on. Yeah, that might also happen. Maybe I haven't drawn the distances clearly. Huh?
That blue is already a center.
Creating three clusters.
Oh, we are creating.
In starting, you chose 3 centers, right?
We start. Yeah. So I'm saying that we are saying we chose the 3 centers to be all the 3 centers to be these ones.
For that first, the middle green,
Hmm.
only the side green will have the shortest distance.
Do we calculate distances from
Only these two will have the shortest distance, not the other points.
Not the other points, but I think the point that is being made is that this middle wala.
You don't find,
I mean, this is also a point,
but it is already a center.
but it's also a point. So you have to reassign it.
So if we initially assign some points to a centroid, do we need to calculate?
Absolutely, yes. See, imagine centroid as only a role that you are playing, right? Centroid may be a point in the actual data, it may not be a point in the actual data, but you still have to assign the points to whatever the centroid.
Center is the blue center is the closest one to the blue point.
The blue center is the closest one to the 2 blue points, yes.
The middle blue.
Yes,
The middle blue is the closest to the middle blue point.
yes.
So it will not get assigned to the green.
No, I think no. I mean, see, okay. Let me sort of because there's a role of a point as a center. There's a role of a point as a point itself, right? What I think is the issue being raised in this particular thing, and I think to me it's a legitimate issue, is that in the example that I said, if I happen to put a center here, happen to put a center here, so in the first iteration the middle green comes to this center because it's on this point itself. Middle blue comes to this center because point itself. Middle orange comes to this center. However, right? Oh, I see. No, I see. That is the point. That is the problem. Yeah. So I think. Okay. So coming to this. So thank you for the counter argument. Maybe that's what you guys are saying. So the middle blue has a center on itself. Therefore, it won't get assigned to the green center because it has a center at distance 0. Is this what you guys have been trying to tell me and I was not listening? Okay, I'm sorry for that. Is the answer to your question clear? There is a center there is already an existing center on the middle blue, therefore, which is at distance 0, and because it is always assigned to a minimum distance center, right, there is nothing that can be lower than 0. So therefore, it will always remain assigned to itself. Therefore, these would be the 3 clusters that are formed, which is actually a bad thing, right? Because this could be, depending on this distance, it could be pretty far off from the optimal, right? So this is not a good thing. What about here? Can k-means do a proper job here? K-means will never do a proper job here, depending on, I mean, however many clusters you give it, right? Because, I mean, it's never going to figure out, I mean, if you assign points to, I mean, it takes a little bit of time to think about it, but if you assign clusters, I mean, anywhere, it carves out things like this, right? It potentially carves out things like this, right? It will never find out these nice clusters. So what do you need to do here? Here is where you need to go to, I'm throwing a lot of terms at you, huh? Here is where you need to go to either something known as a kernel-based distances, right? Or project into higher dimensional space, or we'll see that something like hierarchical clustering, single linkage hierarchical clustering does fairly well here. Okay, but this is not a good set of things for k-means. So now the question for to us is, we saw that there are ways of initializing k-means in which it can really perform badly, right? So what is the natural way of initializing, right? Here is what I'm going to suggest first. Let us initialize using the farthest points. In a sense, what we'll say is that, okay, that let us try to, let's say, choose one center. What we were doing is that we were sort of choosing centers, any arbitrary points, right? Let us try to initialize in which we choose the next center to be the farthest from the, let's say we're choosing center number 2. Then I'll look at all the points, right? And I'll choose the farthest point from center number 1. And I'll assign that as center number 2. Let's say that the farthest point is this one, who knows? Okay. What should I do when I'm choosing center number 3? Farthest from both. Let's say it's this. Okay. Then I'll run k-means. Awesome. I have a great idea. Okay. And at this point, for this one, it clearly converges, right? If this data set consists of 3 clusters that are sort of very far apart from each other, it clearly converges. In case of outliers, this would be a problem. Brilliant, right? That suppose we happen to have an outlier here. We happen to have an outlier here, right? By definition of outliers, there might be, when I choose the first center here, second center might be chosen here, the third center might be chosen here. And third center is chosen here. It might be that it kind of engulfs both of these two, and so on. But this doesn't look like. This is not very robust in the case of outliers, right? Whereas if you think about it, for the case of outliers, because by definition outliers are kind of a small number of them. I mean, if you choose points uniformly at random, you're less likely to choose outliers, right? Because there's only 2 outliers in here. If I were choosing points uniformly at random, I might have chosen something from here, and maybe I'm likely to choose something from here. I mean, because there's only two outliers, maybe I don't even touch them, right? So maybe I should want to choose points uniformly at random, because that is less sensitive to outliers. But on the other hand, I saw that choosing these farthest points kind of gives me a representation of the clusters, nice representation of the clusters. So what should we do? When we are selecting farthest points, okay, good question. When we are selecting farthest points, how do we select the first point? Typically, we do it arbitrarily. The first point we do it arbitrarily, and from next point onwards, we take the, arbitrarily, or you could take, when I mean arbitrary and when I mean uniform and at random, they're slightly different things. In practice, you do, in theory, you do uniform and random, and then you select this. In practice, I think arbitrary works fine. Arbitrary, and then you select this. Okay, so what do we do? So what we do is known as something as making khichdi. See, here is what happens in theory. I'll tell you a brief secret that you sometimes have what's known as a sara hua dal. It's not very good. So it works on something. It is fine in some cases, not in others. You have some not so good rice, right? But sometimes if you mix the two, it turns out to be pretty nice, right? And that is exactly what is going to happen. That we're going to somehow interpolate between these two algorithms, and so we'll interpolate between these two, and that will be a fairly nice algorithm actually, right? And I'll just tell you how to interpolate between these two. So, and we'll do this. This will be what is known as a randomized algorithm. So I don't know if you guys have faced examples of randomized algorithms. So previously, any algorithm that you have likely seen till now is what is known as deterministic, in the sense that given the input data, algorithm knows what to do, right? In the case of randomized algorithms, what it does is that, okay, it looks at the data, and then it says that, oh, I'm not so sure. Let me actually toss a coin. Let me actually choose a random sample out of the data, right? And then do something. That is the style of these algorithms, right? And these algorithms, they kind of work with high probability. So I can say that, okay, this algorithm will sort of give me a good result with 99.99% probability. That's the kind of guarantees that we have. Right? So that's going to be the kind of algorithms. Right? And I'll just tell you what it is, and then we'll go sort of this. What we'll say is that okay, these are the 4 centers you have chosen. Right? These are the centers you have chosen. Right? Now for every point, right, measure the minimum distance with respect to these centers. So this was not a nice picture, but for this point, let's say this is the minimum distance, which is obviously it's not, but think of, so this is C1, C2, C3, C4. So this is the point of x, and this is the distance d of x. Okay? So for every point, measure the minimum distance with respect to these centers. Okay? So now, so for y, this might be d of y. Okay? So now, next time we choose the next center, in terms of the 5th center, we choose it according to this kind of a probability distribution. So what does it mean? Suppose there's only 2 points x and y, then the probability distribution will be d of x to the power alpha. So the next center C5 equal to x with probability d of x to the power alpha divided by d of x to the power alpha plus d of y to the power alpha, and C5 equal to y with probability d of y to the power alpha divided by d of x to the power alpha plus d of y to the power alpha. Okay? If there's only 2 points, then this is the probability distribution. If there's 10 points, then there are 10 such lines. Right? So that's how we choose the next point. Right? What is alpha? I'll come to that. What is alpha? So alpha is my khichdi recipe. Okay? So that's how we choose the next point. Now, how do you go forward? You again recalculate everybody's dx, because now everybody's dx has changed because they've added a new point, right? And now and then you again create this probability distribution and choose sampling. What is alpha? What happens when alpha equal to 0? Every point is uniformly chosen, because alpha equal to 0, all these, anything to the power 0 is 1. Every point is uniformly chosen. When alpha equal to infinity, I'm claiming that this is the farthest point. This is the farthest point heuristic, right? Because you let alpha tend to infinity, again the same kind of things that we were doing. Let alpha tend to infinity, and only the farthest distance, let's say that x is the farthest distance, divide everything by d of x. Let's say d of x is the maximum, right? And then let alpha go to infinity. So you will only be left to the farthest distance, the point in the farthest distance with probability 1. Everything else will be 0. So the farthest point will be chosen. We will use alpha to be equal to 2 for kmeans. Okay? And that will be our kmeans ++ algorithm. And that will perform exceedingly nicely. Okay? So this is what we're going to look at in the next class. Plus we'll talk a little bit about hierarchical clustering. Maybe we'll get to some dimension reduction. Okay. How to choose k here? That's a very good question. We'll talk a little bit about that. How to choose k here? Yes. Any other questions? Okay. Thank you.